So rainfall, as normal rainfall has a pH of 5.6, so it's slightly acidic. That's due to the carbon dioxide. So you have water plus carbon dioxide is going to produce carbonic acid. Now this is a weak acid, so it's not going to have full dissociation. However, it is an acid. So by itself, that's it. But acid rain is something else. So the main thing that makes acid rain are NO2, nitrogen dioxide, and SO2. So when these add up with water, you end up making nitric acid and either sulfuric or sulfurous acid. So H2SO3 is kind of more common. Now, both sulfurous acid is a weak acid, but it has probably close to 70 to 80% dissociation, while nitric acid is a strong acid. So these are the ones that kind of dramatically reduce the pH of rain and have the damaging effects on the environment and on property, all of those sorts of things. So there's kind of two different things there in terms of acid rain. But rain by itself, even if there was no pollution whatsoever, would have a pH of 5.6. So an indicator. So an acid-base indicator is a substance that changes color according to the pH. So sometimes they're weak acids. So we have an ionized and an unionized form have different colors. So depending on what the pH is of your substance, it's going to change color and indicate to you when there's a significant change in pH. So depending on what you have and what kind of situation you're working with will determine the type of indicator you'll use. So these are 4 common indicators. The most important one for us is phenolphthalein, and that's what we're going to be using in our titration experiment. It is colorless or clear in an acidic solution, but pink fuchsia in a basic condition. So that's the most common one that we will use and that you'll be responsible for. Litmus is another important one, which is red in acidic conditions and blue. There are 2 other common ones, methyl orange and methyl red. It just depends on the acids and bases that you're using in order to determine the best indicator. If you go on to take AP Chem, we'll talk more about what's important in terms of picking an indicator to have a successful titration. So when an acid and base combine, the H+ ion combines with the OH ion to form water. So they are forming completely neutral water, so this type of reaction is referred to as a neutralization. It's actually a special type of double replacement. This is if you think back to Unit 5 when we were talking about reaction types, this is a 6th type of reaction, a neutralization reaction. So an acid will react with the base to produce water and a salt. So a salt is just a generic term to describe an ionic compound in this case, so it doesn't necessarily mean NaCl. So in looking at this example, we have an acid plus a base to give our salt and water. So in this case, our salt would be NaBr. There's a wide variety of salts out there, depending on the reaction that you're working with. So sodium hydroxide would be NaOH, reacts with hydrochloric acid, HCl, to produce NaCl plus H2O. So just like before, we would need to balance this reaction. This one's actually already balanced. If you're thinking of phases of matter here, remember water would be a pure liquid, and all of these rest are solutions, so they would be aqueous. The next one is a little bit trickier because it's phosphoric acid, so that's H3PO4, and that 3 is there because the phosphate has a -3 charge. With calcium hydroxide, calcium has a +2 charge, so we need 2 hydroxides to balance it. So we're going to be making water still, but we'll also be making Ca3PO4 2, and we have this 3 and 2 in place because we are balancing the charges plus H2O. Now right now this reaction is not balanced, so you would need to balance it in order to be able to do any sort of calculations with it. So in order to balance this reaction, we're going to put a 3 in front of calcium hydroxide, a 2 in front of the phosphoric acid, and then that will produce 6 waters for us. So you can write out your balancing reaction or your little inventory to help you if you get stuck. So a titration is, we started talking about this in class, but a titration is when you know a concentration of either the acid or the base, and you have one and you don't know to the other. So you're going to slowly add it so that you can figure out what the concentration is of the other substance. So you can use a pH meter to help you determine when it has reached the equivalence point. So the equivalence point is when the stoichiometric amount of acid is equal to that of the base. So you'll also notice that the equivalence point occurs at 7 for us when we're using a strong acid and a strong base. So when we start the titration, in this example here, we're starting with an acid. And we know that because our pH is low, and the base would be in the burette. And as we add it, the pH is increasing, and you'll notice that there's this almost straight up and down portion of the curve. So that's where your equivalence point is going to occur. So that's when the concentration is changing so dramatically that it causes almost a straight up and down line. So just before or after the equivalence point, the pH is going to increase rapidly. So at the equivalence point, the moles of acid equal the moles of base, and the solution contains only water and the salt from the cation of the base and the anion of the acid. So if you continue adding base, you're going to continue increasing pH levels, and it will eventually level off again. So in terms of indicators, so we're going to talk about this in terms of phenolphthalein. So phenolphthalein in an acid would be clear. So down here you would have a completely clear solution. And then at the equivalence point for our phenolphthalein, it's actually about right here. This is where you have a light pink. So when we do our titration, we want to get the lightest pink color possible. And then up here a little bit more, you get a fuchsia or kind of like a hot pink color. So if you get that color, that means that you've gone too far and you're nowhere near the equivalence point. So even though the light pink color is occurring slightly above the equivalence point, because it's such a small amount, makes such a big difference, we are able to use it to help us to determine the equivalence point. So in order to do any sort of neutralization reaction with a titration, you need to write out the balanced chemical equation. And this equation is 1-to-1. And this is the equation we're going to be using in our titration in class as well. So you'll notice that we have 53.24 milliliters of our sodium hydroxide. It tells us the specific concentration. And we're neutralizing 30 milliliters of hydrochloric acid. So the first thing that we have to do is we have to figure out how many moles of NaOH we have. So molarity is moles over liters. So we have to convert our milliliters to liters. So it's going to be 0.05324 liters. So we're going to take our concentration of 0.0025 molarity times 0.05324 liters, and that will give us the number of moles. So that gives us 0.0001331 moles of our NaOH. So then we will do a stoichiometry problem with that. That's the second step. So we'll take our number of moles and go from moles of NaOH to moles of HCl. So again, this is where the balanced chemical equation comes into place, and this is a 1-to-1. So even though it's 1-to-1, we still need to show this stoichiometric relationship and show the math of it. Otherwise, it kind of looks like we're just doing magic, which is not. Magic isn't chemistry. So we have our moles of HCl. We have our volume of our HCl. We just have to do a quick conversion to put it into liters. So we're going to divide that by 0.0300 liters to determine our final calculation. So that gives us a final concentration of 0.00444 molarity of our HCl. So that would be our final answer. Notice I have 3 sig figs because the 0.0300 has 3 sig figs in order to determine our final concentration. So why don't you try the next one on your own and go from there. So you will need a balanced chemical equation. Here's the equation. I haven't balanced it. Why don't you try to balance it if you didn't get the equation? So you should end up with 0.00329 moles of KOH. You then have to do your stoichiometry step. So because this reaction is not one-to-one, this step is essential to make sure that you have your appropriate ratio of 1 to 2. So you end up with 0.00165 moles of H2SO4 divided by 0.030 liters to give you the concentration of H2SO4 as 0.055 molar sulfuric acid. So hydrolysis of salts. So if you take a look at titration curves a little bit more closely, you'll see the equivalence point would not always be the 7. So this is due to the reaction of when the salts are produced. So this is referred to as salt hydrolysis. So I have a table below to summarize what combinations of acids and bases and what's the result of the hydrolysis. So what you're kind of doing, so let's take a look at a few examples. So in this first one, let's look at NaNO3 would be so that would be produced from sodium hydroxide and nitric acid. So taking a look, the sodium with water would produce NaOH. So this would be a strong base. Strong bases fully dissociate, so you know that this isn't going to be an issue for you because it's fully dissociating. It's not going to be an issue. NO3 does the same thing. This is a strong acid, so if you have a strong base and a strong acid, the resulting salt will be neutral. So if we take a look at the next example, so we have acetate. So acetate, this would be producing a weak acid, and ammonium would produce ammonia, which is a weak base. So both of these would result in a partially basic or partially acidic solution. So because the weak acid isn't going to fully dissociate, it's going to result in a salt that is slightly basic. So it would produce a basic salt. So if you had, for example, NaC2H3O2 as your salt, this would be a basic salt because of the weak acid that would be formed by the acetate ion. If you had something with ammonia in it, or ammonium, that would produce a acidic salt. So it's the opposite of what the weak one would be. So if we had NH4NO3, this would be an acidic salt because the ammonia would produce or the ammonium would produce ammonia, which doesn't fully dissociate and produces some hydronium with it. So this is a nice little summary table. So what you're looking at, I always look at the salt that forms and think of what would it produce. Would it produce a weak acid or a weak base, or a strong acid or a strong base? So if you have two strong acids and bases, you'll have a neutral salt. If you don't, if you have a weak acid, it's going to produce a basic salt. If you have a weak base, it's going to produce an acidic salt. So this last category, if you have both a weak acid and a weak base, you have a lot of options of things that can happen. I'm not going to ask you questions like that, but if you go on to take AP Chemistry, that would be something discussed. There is calculations that you can do to figure out what would happen. We just won't do that. So we're going to kind of focus on the first three here. So you could have a strong acid with a strong base, a strong base with a weak acid, or a strong acid with a weak base. I'm not going to ask you specific pH values that they would produce. It's more of, is it acidic, basic, or neutral? And what is the reason for that? So is it because you have a weak acid, a weak base? You know, what's happening in your reaction?